Yes, so let's move on towards our lecture number 21 of physics optional paper 2 for UPSC CSE. Okay, paper 2 physics optional lecture number 21 up to lecture number 20 we have done uh, whatever you saw we have done. Okay, so if you haven't watched the previous videos, then you must go and watch the previous videos if you in case you are new to the channel. Okay, and if you are not new to the channel and you have been watching the videos regularly, then there is no need to go to the playlist. Okay, so it is about the person who has visited the, it depends on them. Okay, so let's start our lecture number 21. Lecture number 21 says wave functions. Just put the heading wave functions for realistic situations. Wave functions for realistic situations. Someone was asking me, someone was asking me that you said you have done this three times. Someone was asking me, you have done this three times. Uh, first in first time in this, then second time in this, third time in this. Okay, and then after this, in the third time, you did this, and then you qualified net. Okay, CSIR net exam. So why have you done it three times? The person was asking me. Because you have, isn't it a waste? Because you have utilized 2 years here, you have put 2 years here, and you have put 2 years here. Let me tell you one thing. You must have seen a person, a 60-year-old graduate. You must have seen 60 years old person taking degree. You must have seen such persons. They come in the news often, taking degree. So ask him that why you are already 60 years old, your children are married, and you are taking degree. What's the use of that? What's the use of that? So he simply replies that it's my passion. He simply replies that it's my passion. Okay, I love to take degree, so that's why I am taking it even at the age of 60 years. Okay, so there was a person in some university. He was asked in the interview this question only, that you are 60 years old already, your age is declining. You must go towards retirement, and you are taking degree. So what's the use? Okay. So he was saying that just out of interest I am taking. So that's why I have taken this, done this three times, and it helped me a lot. I was the in the offline mode at Delhi. I was the only teacher who knew all the three subjects. Okay, I was the only teacher who knew all the three subjects at Delhi Offline Coaching Institute, and my salary was 3x because of it. My salary was 3x because of it. Okay, so you, whatever you learn in life, it never goes waste. Okay, so remember this thing. And also, if I tell you my UPSC journey, then 2011 I had optional. Okay, before 2013 there used to be two optionals in UPSC. Then in 2012 my optional was this. Okay, then so on and so forth. Then up to 2016, then in 2016 my optional was uh, maths. But before that, in the year 2015, my optional was physics. Okay, then in and so on and so forth, like that. It was always between these three subjects. Okay, I switched over between these three subjects, seeing the previous year result. Okay, so that's the thing. I have lived these three subjects. Okay, I have lived these three subjects. Okay, PCM runs in my blood. Okay, it runs in my blood. Okay, so that's the thing. That's why I have done it. At that time, many people laughed at me, but I ignored. Many people laughed at me at that time, but I ignored them. I just ignored them. And no one had that much salary. I had 3x because a person was only teaching this. or either only this or only this either. I was teaching all the three, so 3x was the salary. Okay. So anyways, uh, uh, we will discuss it sometime later. Okay. So for realistic situations, stationary system, stationary system, state of the system. Now, what is a stationary system? Stationary system is such a system that its state, okay, state of the system does not change with time. State of the system does not change with time. What does this mean? This simply means that it is time independent. Okay. What does this mean? It is time independent. Okay, because it does not change with time, so time expression will not come in its time variable will not come in its expression. Its wave function expression will not contain time. Okay. So wave function for stationary system, wave function for stationary system, wave function for stationary system. Okay, it is represented by this. Okay, or you can call it, it is only a function of r, as it is only a function of r and not of t, so it is being represented by small psi. If it would have been a function of both r and t, then it would have been represented by capital psi. And what is the difference between capital psi and small psi? How they are written differently, I have already told you in the preceding classes, right? So this is in 3D space. Okay, in 3D space means it has all the three dimension x, y and z, so it is in 3D space. Okay, it is in 3D space. And when we restrict it to one dimension, okay, when we restrict it to one dimension, suppose these are also possible, but these are not usually taken. Okay, these are also possible. Okay, it is not necessary that you will always take x direction only. Sometimes only z or only y may also come, but usually this is the most common notation. This is the most common notation in for one dimensional. If there is motion in y direction only, then we consider that y direction to be x only usually, and we represent it like this only instead of representing it with y. Okay, that is a standard notation to represent it with x. Okay, because these three coordinate axes are interchangeable in space. Okay, because these three coordinate axes x, y, z are interchangeable in space, right? X, y, z are interchangeable in space. Either I may if I want I may call this type, or if I want I may call it like this also. If I want I can call it like this also, right? So all these are possible, right? So that's why the thing is like this. And then again there are a lot of combination possible, so that's why in one dimensional space, sometime if the examiner wants you to concentrate too much, then he may give you psi y or psi z instead of psi x for one dimensional space. But it is very rarest of the rarest event that we are representing it like this. Okay, it is rarest of the rarest event. Okay, so this is the thing. Now this is what is Schrodinger time independent equation has come over here, because it is not depending on time. So its expression, algebraic expression, will not contain the time term in it. It will only contain the r term if it is three dimensional space, r vector term. What is r vector? R vector is position vector, right? R vector is your position vector, x I cap plus y j cap plus z k cap, right? R vector is your this x I cap plus y j cap plus z k cap, right? And this is one dimensional space, this is three dimensional space. Okay, And one more thing is there, that it is a stationary system. Stationary system means we have assumed the time has paused. Okay, time has paused, we have assumed. Either we have assumed that time has paused, or we have assumed that it is independent of time. Okay, independent of time. Okay, independent of it. Now, what does this imply? I had already told you in the Bohr's quantum condition that we had a standing wave. While we studied the Bohr's quantum condition, de Broglie hypothesis, from de Broglie's hypothesis, we arrived at the Bohr's quantum condition. At that time, I had already told you one thing, that it was a standing wave. The wave inside an atom was a standing wave. So it was independent of time. Okay, it was independent of time. Similarly, this will be a standing wave. It will be independent of time. Okay, now how does independent of time imply standing wave? Because wave will propagate with time, right? Suppose this is the thing at t equal to 0, then at t equal to 1 such situation may arise. Okay, such a situation may arise at t equal to 1, right? So the wave has traveled like this from here. It has traveled up to here. Okay, up to where? Up to here it has traveled. Okay, it has traveled up. Suppose it is traveling in this direction, then the wave has traveled this much. Okay, this much the wave has traveled. So after the wave goes that much forward, you can clearly see that it will become like this. Okay, so a propagating wave will propagate with time, but it is time independent, so it will be a standing wave, means it will be stationary. Okay, stationary. If it is like this, then it will be like this only, always. Okay, so that is the thing. So condition, now we will move on to the condition to be satisfied by the wave functions for realistic situations. Okay, we will move on towards this, that conditions to be satisfied by the conditions to be satisfied by the wave functions for realistic situations. Okay, for realistic situation, we will move on towards the conditions that must be satisfied by the wave function for realistic situations. Okay, so number one is psi x. Okay, condition number one is like this, as well as del psi x by del t must be finite everywhere, must be finite everywhere for all values of x that is in the range minus infinity x to plus infinity. So psi of x as well as del psi x by del t must be finite everywhere for all values of x. Even if we even if we put x equal to minus infinity in this expression. Okay, even if we put x equal to minus infinity in this expression, even then it must yield you finite value. If we put x equal to minus infinity over here, even then it must yield you a finite value. If we put x equal to infinity also, even then this should yield you a finite value. And even if you put x equal to infinity over here, then it should also yield you a finite value. Got it? So these are the conditions to be satisfied by the wave function. This is the first condition. Okay. Now in the range minus infinity to infinity means all the real numbers have been covered in it. Right from the very negative to the positive numbers and very large numbers to very small numbers, everything has been covered. Every real number has been covered. Now x value should be real only. For complex x, for example, you cannot put, okay, you cannot put x equal to iota over here. Okay, you cannot put x equal to iota in these functions, it will be wrong. Okay, because you are dealing with realistic situations, so you are dealing with realistic situations, so that's why the values of x will be real only. Okay, so now we will learn the proof of this. Okay, so suppose you have psi x at x equal to a is equal to infinity. Right now I told you that infinity value, these values must be finite. Okay, right now I told you that these values must be finite. Which values? I told you, right? Psi of x and del psi x by del t. Okay, these must be what? Finite, right? I told you right now. But if suppose these must be finite, now if I put some value of x and if I get infinite, so this wave function is not possible. I need to show that for x equal to a, this wave function yielded us infinity, so it is not finite value, so it has violated our condition number 1, that it has come to be infinite, so it has violated our condition number 1. So as it has violated our condition number 1, so we are checking that really some contradictory result comes or not after putting x equal to a. So after I put x equal to a, this thing will become psi x square. What is this psi x square? Psi x square is basically your probability density. Okay, psi x square is your probability density. This is the psi x value at x equal to a, and psi x square value is equal to your probability density. Now as psi x value is equal to a at x equal to a, psi x value is equal to infinity, then psi x square value at x equal to a will also be equal to your infinity only. Okay, because you will simply take the square of infinity, and square of infinity is again infinity. So this will be contradictory. Why this will be contradictory? You only tell me that suppose if probability density at a particular point x equal to a, probability density at particular point x equal to a, suppose it is infinity, then it is sure shot, that the particle will be found there only. Okay, it will be big, it will be a surety, then it will be a violation of Heisenberg uncertainty principle clearly. Okay, if I say that a particle has infinite probability of being found at x equal to a, then certainly uh, it will have infinite probability, surety, because infinite probability at x equal to a implies surety. Okay, so if it is sure that it will be found there, then it will be a violation of quantum mechanics, because quantum mechanics says that it is wrong to say that a particular thing is present at particular microparticle such as electron or proton is present at a particular place. Exact coordinates of electron you are telling, that in itself is wrong. That is what says the quantum mechanics. Okay, quantum mechanics clearly says that you can't you can't talk about surety in quantum mechanics. It is a fundamental of quantum mechanics, that you cannot talk surely about any microscopic particles such as proton, neutron, electron, etc. Now over here at x equal to a, infinite probability has come, so clearly it will be like that the electron is sure to be found, 100% surety that it will be found at x equal to a. So it has become basically your classical concept, but this is a contradiction to quantum concept. So clearly we can imply this basically implies that particle is completely localized. Okay, particle is completely localized at x equal to a. Okay, this contradicts basically. I had already told you in the previous classes that the particle can be found anywhere within the wave packet. Particle can be found anywhere within the wave packet. So saying that it will be found at exactly x equal to a contradicts the very wave property of the particle. So this clearly contradicts the wave property of the particle. Okay, contradicts the wave property, contradicts the wave property of the particle. Okay, okay. So this is the first condition. Now the second condition is psi x and del psi x by del x. Okay, del psi x by del x must be single valued. Okay, must be single valued. Let us understand the proof of this. Okay, this must be single valued, it is saying. So let us understand the proof of this. Okay, let psi x is equal to psi 1 psi 2. Okay, psi 1 psi 2 psi 3 etc. up to psi n. Okay, although it is not a reality, but suppose I assume that the stationary wave function psi x has n discrete independent forms of wave function. Okay, these are independent waveforms. Okay, independent wave functions. Suppose a single particle stationary in time. Okay, suppose a single particle stationary in time is being represented by n independent wave functions. Okay, so particle is being represented by n independent wave functions. So it is clear that uh, we can write like this, that how to write this in statement. Okay, suppose a quantum particle, suppose a quantum particle stationary, suppose a quantum particle stationary in time. Okay, suppose a quantum particle stationary in time uh, is represented by n independent. Okay, n independent wave functions. Okay, n independent wave functions. Suppose we assume like that. Okay, where okay, yes, so is represented by independent wave functions. Okay, then you can clearly see this thing. These are independent wave function means when a constant is multiplied. Okay, so this type of relation is not possible between them, that this is the case, or psi n is equal to psi 1 divided by 38. Such relations between these are not possible. Means multiplying by a constant and dividing by a constant and then writing them, they will be dependent functions. Okay, but over here we are talking about independent wave functions. Over here we are talking about independent wave functions. So these are n independent wave functions. Okay, so it is a particle is represented by n independent wave functions. Okay, so then the probability, now these are at x equal to x, means at the same place. Okay, at the same place also we should write at x equal to x we are talking about. Okay, so at the same place, let's write over here at the same place, at the same coordinate we should say. Okay, at the same coordinates, उसी कोऑर्डिनेट पे और उसी टाइम पे. ओके, एट द सेम टाइम एट द सेम कोऑर्डिनेट these two functions are there, these n functions are there, which are representing a single particle, and we are deliberately assuming this wrong statement so that we can prove it wrong. We can prove the second condition. That's why we are assuming this wrong situation. Okay, because as there are n independent equations, so it is clearly contradicting our second condition that they must be single value. So deliberately we are basically proving by contradiction method. Okay, proving by contradiction. We are proving by contradiction that suppose there are n independent wave functions, then clearly some ridiculous thing will happen, and as some ridiculous thing will happen, so clearly our condition number 2 will be proved then, that after proving that there are n independent equations, some ridiculous thing will happen, and after that it will be proved that our second condition is second condition is true indeed. Okay, because after assuming these to be multi-valued, after assuming, what are we doing basically when we are saying that psi x is equal to all these? We are saying that we are taking psi x to be multi-valued. Okay, multi-valued we are taking. Multi-valued means at the same time, at the same place, at the same coordinates, at the same time we are taking this, and we are saying that psi x is multi-valued. Multi-valued means it has n values. Okay, it has n values. So the thing which will contradict this is that then probability density. Okay, then probability density at same point x equal to x at all time t, at the same point x equal to x, probability density at all time t. Okay, at all time t means time is stationary over here. Okay, so we are not assuming the time term. So clearly by the Max Born interpretation, your probability at the same point x1 will be equal to this also. Okay, your probability at the same point x will be equal to this also, because there are n independent wave functions associated. As there are n independent wave functions associated, so your probabilities will be like this. Okay, and so on and so forth, and so on and so forth up to rho n is equal to psi n square. Okay, now clearly rho 1, rho 2, rho 3, and so on and so forth up to rho n, what do they represent? Probability densities at the same point x at the same time. Probability densities at the same point x at the same time. Okay, so you only tell me, now we have already taken that psi 1 is not equal to psi 2, is not equal to psi 3, is not equal to psi 4. We have already taken this. Okay, and is not equal to psi n. Why we have taken this? Because these are n independent wave functions we have assumed. Okay, as we have assumed, if they would have been dependent wave function, then they would have been equal. If they would have been dependent wave functions, then they would have been equal. But as we have assumed n independent wave functions, so that's why this is the situation which has arose. That's why this is the situation which has arose. Now corresponding to psi 1, as these values are not equal, and you have already told that rho 1 equal to this, rho 2 equal to this. So clearly, as these are not equivalent wave functions, they are independent wave functions. Independent wave functions means they cannot be obtained by multiplying or dividing something. Okay, they cannot be obtained by multiplying or dividing by a constant. They cannot be एक दूसरे की वैल्यू कांस्टेंट से मल्टीप्लाई डिवाइड करके नहीं आने वाली है, राइट? Each other's value will not come after multiplying or dividing by a constant. So that's why these are independent wave functions, and as these are independent wave functions, so these are not equal. So clearly, by this also, rho 1 will not be equal to rho 2, will not be equal to rho 3, and so on and so forth, and will not be equal to rho n. Okay, now tell me one thing. At the same point, so at the same point at the same point in space, at the same time, at the same point in space, at the same time, we have n probabilities, probabilities nahi, probability densities. Okay, probability densities I should write. Okay, we have n probability densities which are not equal. If they would have been equal, then it would have been good, it would have been all right. But at the same point, at the same time, okay, a single particle, same particle has n different probabilities. It is very ridiculous. Suppose if you have a coin, suppose you have a coin, and there are two chances of heads and tails. You have a coin, suppose सिक्का है आपके पास, and you have two probabilities that either heads will come or either tails will come. Now someone says that the probability of head coming is 1 by 2 also, and 3 by not 3 by 2, sorry, 1 by 3 also. Someone claims that the probability that a head will be overturned when this coin is tossed. This is an unbiased coin. When it is tossed, someone says that the probability that head will come is 1 by 2 also and 1 by 3 also. Then how is this possible? Probability will always be 1 by 2 only, because it is an unbiased coin. So that head will come upwards, head will come upwards, that will have only 1 by 2 probability. How can it have 1 by 2 probability also and 1 by 3 probability also? It cannot have. So similarly, at the same point, at the same time, for the same particle, n probability densities, and that too n distinct probability densities. This is not at all possible. Okay, so this is completely unphysical situation. That implies that this is completely unphysical situation. As it is completely unphysical situation, so clearly, as it is a completely unphysical situation, so our assumption that the same particle at the same time okay, at the same place our assumption that the same particle at the same time and at the same place has n different wave functions associated with it is wrong. So our assumption, what assumption? Our assumption that at the same particle at the same time and at the same place has n different wave functions associated with it is wrong. Okay, So what does this imply? This implies that psi x will be single valued. Okay, now as psi x will be single valued, so it is quite obvious that del psi x y, del psi x by del x, this will also be, this in turn implies that this will also be single valued only. Okay, this will also be single valued only. So this was all about the second property. We have four properties. Actually we have four conditions that must be satisfied by wave function for realistic situation. We have actually four conditions that must be satisfied by a particular wave function in order to that wave function to denote a, so that we have four different conditions for this, for a wave function to be realistic. Okay, only if it satisfies the four condition, only then it will be realistic. So we have satisfied, we have basically proved the two conditions. Okay, 1 and 2. Now the condition number 3 and 4 I will do in the next class. Okay, conditions number 3 and 4 we will do in the next class. So तब तक के लिए जय हिंद जय भारत, अपना ख्याल रखें, टेलीग्राम ज्वाइन कर लें.